Hi all. In this video, we are going to see about paper titled "Continued Version of the Nestro Accelerations" for accelerating stochastic gradient descent method applied to machine learning. So, what this paper is detailed about, or overall view of this paper. So, we all know that many factors have given a success of machine learning, especially deep learning. One of the important factor is first order optimization method developments, which usually require a low cost per iterations. But since the conversion rate is a bit low, many acceleration techniques have been introduced to in order to make the convergence rate as fast as near to the second order method like Newton-Raphson method. So one of the acceleration techniques we all know that seminal work of Nestro. So this is the equation one is the criteria for a convex optimization. If the function to be optimized is a convex, and equation two is a criteria for a strongly convex. And we all know that a gradient descent method uh, have a first order convergence rate for the smooth case. But if we apply acceleration technique like Nestro method, it can go to the level of second order similar to the Newton-Raphson method, but requires certain criteria to be satisfied. So, what is Nestro acceleration techniques? So, this video assumes that people have some basic understanding about acceleration techniques, but later part of the this paper we may introduce detailed study about what is acceleration technique for the gradient descent method and what is Nestro acceleration. So, usually the Nestro acceleration involves per iterations like 2 to 3 steps or sequences. These one of one only one step is a gradient step. The other steps are mixing steps where it has an in between algebraic equations, discrete equations, which introduce more intermediate variable. That intermediate variables helps to update the gradient steps. So in this paper, large attempts have been provided to this paper have attempted to develop a continued version of the instruction. It means that instead of the discrete, that mixing step, it has a continuous ODE equations. So this also paper introduced a continuous version of Nestro accelerations. So this because of this continuous Nestro acceleration, the gradient steps involve some random parameters. So because of the random parameters, it has the gradient steps happens at random time steps. It's not like a sequentially at all times. So it happens at random times at T1, T2, and T3. So it means that mixing step, that intermediate discrete ODE equations and the gradient steps involved per iterations, and it occurs that gradient optimizations occurs randomly. So it involves stochastic optimizations. We all know that one of the reason for the success of optimization methods is for a deep learning method is a stochastic optimization, which helps us to escape from the local minima. So it not only stops here. When we describe the continuous version of this mixing steps, it ends up with exactly the same form as algebraic Nestro acceleration techniques. These are discrete techniques. So it closely mimics the original version of the Nestro accelerations when we entered into the discrete part of the continuous versions. In addition to that, introducing the stochastic parameters that are happening at the random times, it also helps in developing this, setting up this acceleration techniques or gradient optimization methods in an asynchronous parallel computing, which helps improve the computational time. So if we are having if we don't have this random time steps, then we cannot have an asynchronous parallel computing because each and every node which is happening a parallel computations, one or the other way requires to know something knowledge about the gradient update. But here the happening at the random steps, it not necessarily have to depend upon those gradient steps at the previous uh, case steps. So it helps in randomization. It helps in establishing a stochastic optimization. Also, this continuous discretization helps in setting up an asynchronous and distributed behaviors, which helps us to setting up an asynchronous parallel computing, and also end up in a stochastic optimization problem. So this not only improves the convergence rate, like escaping the local minima, it also helps in improvising for an asynchronous parallel computing. So this is the crux of this paper. And previously, many attempts has been done for introducing these randomizations through continuous version of that. Many papers have been introduced here, but all to be claimed here that it is purely not asynchronous, purely asynchronous way. Or this is one of the paper which includes the asynchronous way, so that distributed parallel computing gossiping setup can be improvised. So this in altogether, this paper is a continuous framework, but it helps in making a decentralized optimization in a asynchronous way. And when we discretize, it mimics exactly the same set of original discrete Nestro accelerations. So this paper is sectioned as this. Section two will like later part of the this paper, maybe in the next video we will try to introduce what is gradient descent acquisition basic version, basic fundamentals. Then we will then this paper introduce the continuous version of the Nestro accelerations. Then how the discretized continuous acceleration can be exactly similar to that of discretizing will be technically similar to original versions, and also introducing of the random parameters will helps to set up a stochastic gradient descent. And also it can be very well suited for an accelerated asynchronous algorithms for the gossip problems. And finally it can go for a decentralized optimization setup in section 7. Hopefully we'll try to see all these sections in detail in later part of the this paper series. Thank you.